In this video, we're going to explore addition and subtraction at Key Stage 1, and in particular, the prevalence of the formal written algorithm, and ask the question as to whether it's actually necessary for pupils of 5 or 6 years old to be able to use it at all. So here we can see the requirements in England for the end of Key Stage 1 in reference to addition and subtraction, and we'll usually find that this section here is interpreted as meaning pupils need to be able to use the standard written algorithm. And I think we can show that that's not necessarily the case, and rather our time should be spent on developing pupils' mental methods and their mathematical flexibility with number, rather than on arbitrary or more abstract algorithms on which we can spend our time much later in our pupils' education careers. And so to do this, I brought in the help of Christopher Such. He's going to take us through some of the methods that he would give priority to over the formal written algorithm. Over to you, Christopher.
While it's no doubt possible to get children in year 2 to add and subtract two-digit numbers using column methods, it isn't necessarily a good idea. In fact, in the vast majority of cases, I would argue that it isn't. Now, the reason for this is because what we really want is children to develop an array of mental methods from which they can choose that are built upon the sound foundations of the field axioms, which they'll be just beginning to grasp, and their understanding of equivalence. Let's see what I mean by that in practice. With regards to mental addition, the most common way that we support children to deal with addition is that we often say, well, let's break two-digit numbers into their tens and ones, and then let's deal with the tens together and the ones together. Now, this way of dealing with things is obviously built on the field axioms. It's built on the idea of associativity in particular, as you can see here, and it does and can lead to formal column methods at a later stage. But at this point, I'm much happier with children seeing the numbers being broken down and seeing how they can be added, including perhaps understanding this through the use of manipulatives, such as Deans. But we can also look at addition in other ways. So, for example, what is sometimes termed place value jumps, whereby one addend, usually the smaller one, is partitioned and then added in stages to the other addend. Equally, we can think about the idea of friendly numbers, perhaps not the most mathematical term that I could have chosen, but one that I quite like to use with children, which is whereby we look at the same addends here and say, well, is there a way that we can play with these to make them easier to add together? Again, it's where the field axioms come into play. 46 can be seen as 44 and 2. The 2 can then be associated with the other addend, effectively moving 2 from one addend to the other, leaving us with 44 and 40, something children can add mentally, assuming their place value understanding is sound, which it absolutely has to be before they tackle two-digit arithmetic anyway. It doesn't have to be that way round. Equally, we could play with the number 38 and create 34 and 4. Part of that would then exchange over to the other addend. Effectively, we can see that as 4 moving from one addend to the other to create 50 and 34. Again, something that can be added mentally, assuming children's understanding of place value is sound. This idea of playing with numbers rather than having a particular algorithmic way of performing a calculation is just as valuable for subtraction. Place value partitioning is a way of looking at things that eventually leads to column methods further down the line, ideally in Key Stage 2 in most cases. And we can see here that it can be used to subtract 57 from 83, though of course 83 would need to be partitioned into 70 and 13, assuming we don't want to introduce children to negative numbers, which is obviously something that we almost certainly don't want to do at this stage. We can also think of this in terms of place value jumps, where the subtrahend is subtracted in 2 stages. The 50 can be subtracted first and then 7, though it works equally well either way round. We can also use this idea of friendly numbers with children. So if we're subtracting 57 from 83, Perhaps it's valuable to see 83 broken down into 60 and 23, because 57 is so close to 60 that it's actually it's something that we can subtract mentally, leaving us with 23 and 3, which is clearly 26. We can also use the idea of constant differences to make friendly numbers. So for constant differences, here's a visual representation just to remind you what that might look like. So 5 minus 1 equals 4 can also be seen as 6 subtract 2 equals 4 as giving us the same difference. 7 subtract 3 would give us the same difference. 8 subtract 4 gives us the same difference, etc., etc. So we see that if we add or subtract the same amount from the subtrahend and the minuend, we keep the same difference. Now this is a really powerful idea. We can use that in this case to turn 83 subtract 57 into 86 subtract 60, knowing that it will give us the same difference, in this case, the missing number, the answer that we're looking for. 86 subtract 60 is, of course, something that we can do with mental arithmetic. Naturally, not all children are going to become fully confident with these methods by the end of Key Stage 1, so they do need to be consolidated through Key Stage 2. What's important is that by teaching children that numbers are things that they can play with, that they can manipulate in order to make calculations easier, they can learn how to deal with addition and subtraction efficiently depending on the particular calculation that's in front of them. Something that's a far cry from simply learning one algorithm and mastering it.
Thank you, Christopher. So what we've seen already is that when we have combinations of 1 and 2 digit numbers and we want to add or subtract them, we don't need to use the formal written algorithm. And in fact, we can have pupils with a much better understanding of number when we focus our attention on alternative or mental methods and strategies. And the same applies for the addition of 3 one-digit numbers. And we'll just have a look now at both how we can develop a sense of the approach mentally, just one possible approach, because I'm sure there are many, and then how we might represent that with concrete resources, because obviously concrete resources are named especially in the requirements, meaning that we should utilize them when we can, because our pupils are still making meaning of the relationships they encounter. And so there's no reason we should go completely abstract too soon, because that'll probably end up being detrimental to their development. So let's just move this. And imagine we wanted to add 3, 5, and 7. Depending on which 3 numbers we want our pupils to add, the approach will be slightly different. And what we'll want them to do is to be able to recognize when a variation of the approach is most suitable. Because if they have that flexibility of thought, then they will be able to make the right decision or the most efficient decision in the moment. And so here, if the pupils understand and are looking for the bonds to 10, then very quickly they can say, okay, this isn't 3 add 5 add 7. This is really 10 and 5. And then 10 and 5 is a much more manageable proposition than a count all scenario or a written algorithm for 3 add 5 add 7. And so we should expect our pupils, once we have focused on developing this kind of approach, should be able to do this calculation quite rapidly. Okay? And so it's make a bond to 10 and then add what remains. And if we look at these concrete resources, we can see that process where we've got 3 and 5 and 7. We make a 10, and then we've got 10 add 5, just like we did last time. But sometimes, and I've used double-sided counters here, but we can use multi-fixed cubes, I will ask the pupil I'm working with to stack the 10. So then that mimics the mental process. Here we've used, it's almost like an inverted 10 frame. What we can do is ask them to hold that chunk of information, the fact that 3 and 7 is 10, and then move on to the wider picture. And it's because that mimics the mental process. we've got a new chunk of information plus 5. And then from there, that becomes a rapid process in our pupils' minds. And what we're doing is we're modeling each of the steps in that process so they can practice it and assimilate it and make it their own. Now, the numbers we add won't always neatly fall into that make a bond to 10 category. So here we've got 8, 6, and 7, but the approach is very similar. We look at the 6 and we realize that we can make the bond to 10 with 2. And from the remaining 4, we can make another bond to 10 with 1 remaining. And so our pupils go through steps. So we've got 10, 10, and 1. So there are a few more steps. The pupils really need to understand the bonds to 10 and the bonds that are contained within a given number. So 6 can be broken up and recomposed in many different ways. But here, being able to see that actually I need 2 from the 6 to make my first 10 is the decision the pupils need to make. And so again, if they've spent a lot of time in year 1 reception exploring the 6ness of 6, then this becomes a reasonably straightforward idea. And so I think the time we invest in that mental flexibility and the knowledge of an understanding of the numbers that we're working with, because the number 6 is quite small, but to know that it is 0 and 6 and 1 and 5 and 4 and 2 and 3 and 3, if we spend time on that, this kind of process becomes much more easily accessible. And again, if we want to represent that, I've used double-sided counters, but we could easily just use unifix cubes as well. And so we make our 10, our second 10, and we've got 1 remaining. And just like that, we have got 3 chunks of information which we can put together to make the sum. And so hopefully what we've shown is that we can get the whole way through Key Stage 1 without having to cover the formal written algorithm. And in fact, pupils who are able to operate on this level, where they are thinking about the composition of number, where they're thinking about how they can use what they know to help them solve problems, are operating on a higher level than a pupil who is taught to use the formal written algorithm, but there isn't as much time spent on actually what's happening and why things are happening the way they're happening. And I think there's plenty of time in year 3, year 4 to cover formal written algorithms, but I think our pupils are better served if we focus on what's really important and what will make them mathematically proficient